From late 2002 on through 2003, the PC gaming world was focused on the battle between two graphics architectures: NVIDIA's NV30 and ATI's R300. Now, these are both a little bit later models. This is a Radeon 9800 that came out a bit later, and this is one of the later 5900 PCX that has the extra the PCIe to AGP bridge chip, but they're still representative of these architectures. These two architectures help solidify the age of the GPU. The previous generation of graphics chips was also programmable, but it was really limited. The R200 and the NV20 both supported vertex shaders, but there was a limit of, I want to say, 128 instructions. There was no flow control of any kind, no loops, no branches, nothing. There were some very primitive, like conditional select kinds of things, but it was pretty rough. In DirectX 8, this was supported by Vertex Shader Model 1.1. In OpenGL, it was supported by a primitive assembly language-like interface called ArbVertex program. Now, the fragment shading pipelines, pixel shaders in DirectX speak, were even more limited. Generally, only at most 12 texture operations were possible. This gave dependent texturing, where the result of one texture lookup could be used in the next texture, and that was a brand new mind-blowing thing. There was some weird functionality along these lines on some workstation cards. There was an SGI extension called SGI Pixel Texture, I want to say, that you could do some things with, but it was super primitive. The Matrox G400 cards had a bump map mode where they could do some very primitive dependent texturing things, but NV20 and R200 gave real dependent texture lookups for the first time, and this was a super big thing. But with those few texture lookups, you kind of got at most about 30 total instructions. This is literally a very hand-wavy generalization. It's a bit more complicated than that, and there was some variation between the chips, but it's close enough for this discussion. Now, in DirectX 8, this was supported through Pixel Shader Model 1.1 through 1.4. In OpenGL, there was no standard way to access this functionality. There are various reasons for this, but it's way beyond the scope of this video. In my opinion, the executive summary is there are only so many hours in a day, and everyone had much bigger fish to fry. If I ever do dedicated videos about the Radeon 8500 or the GeForce 3 or the GeForce 4, I may cover this in some more detail. Let me know in the comments if you're interested in hearing about this. Now, the NV20 and the R200 were technically GPUs, but just barely. And I take a pretty hardline definition of GPUs. People have come to use GPU as just graphics card, graphics card that can do 3D. But to me, a GPU is something that the application developer can run their own programs on the graphics card. And that requires some kind of shader support, unless you have something really exotic like the old Texas Instruments TIGA cards, but that's also a completely different kettle of fish. That is also another video that I really hope to do someday. The programmability of the NV30 and the R300 was a really huge leap ahead, but as we'll see, it was still pretty basic. The new Vertex Shader Model 2.0 included some very basic flow control. R200 has really, really rudimentary loop support. Basically, you can say, it ends up being encoded outside of the shader that it says, this block of instructions, do this over and over again some fixed number of times. And I think on the original R300s, you might not have even been able to access the loop index. I don't remember for sure. But the loops definitely could not be nested, and there was a fixed number of total loops that could exist in a shader. And there was no conditional branches or function calls at all. Now, NV30 in Vertex shaders had quite a bit more generalized flow control. They have fully general conditional branches. They have function calls, so the conditional branches could be used to create arbitrary kinds of loops. You could have function calls. There was some level of nesting of function calls. I think the function call stack was maybe 16 deep. So if you're really adventurous, you could maybe even have recursion. It was still limited, but it was quite a bit more advanced than what R300 can do. I don't think any of that ever got exposed in DirectX. But in OpenGL, the extension NV Vertex Program 2 basically exposes all the capabilities of the hardware. So if you want more details about what exactly that hardware can do, you can look it up in that extension specification. Now on the fragment side, things were quite a bit more restricted. Pixel Shader 2.0 and ARB Fragment Program exposed a much richer set of instructions, but notably missing is any notion of flow control. Now, NV Fragment Program, which is sort of a little bit of an enhancement over ARB Fragment Program, does expose a condition code register that can be used to emulate some kinds of if-then-else structures, but loops were still, out of the question. Now, as an aside, the ARB Fragment Program extension was approved by the OpenGL ARB at the September 2002 meeting. Now, this meeting was special for another reason. It was the very first meeting that I attended. At that time, I was working at IBM, and I went down to Austin, and I want to say that meeting was that Dell hosted that meeting. But anyway, it was my first exposure to see how the sausage is made, so to speak. Now, even with all of this new functionality available, developers wanted more. They dreamed of more advanced functionality, loops and conditional branches and function calls. And people were already looking forward to the next generation of hardware with high hopes. Most consumers and a lot of software developers were completely unaware that such hardware already existed. And it wasn't in some R&D facility or secret government lab. It was on store shelves. This GPU architecture, known as the 3D Labs P10, first shipped in late 2002 in the Wildcat VP970, the Wildcat VP870, and the Wildcat VP760. The first two cards shipped with 128 megs of 256-bit wide DDR, and the third shipped with 64 megs. Now, this is pretty similar to how ATI split up the Radeon 9700 and the Radeon 9500, which were the first R300 cards to be released. Now, VP in the model is short for Visual Processing Unit. They wanted to differentiate themselves even more. Now, the first reason you probably didn't know anyone who had one of these cards back in the day. The MSRP for the 970, which was the top of the line 120 megabyte card, was $1,200. Now that's basically 3 times the MSRP of the Radeon 9700 Pro, which was already, $400 in late 2002. that was a pretty good pile of money. When those cards came out, I didn't get one. I kept using I think at that time I had a Radeon 8500 LE, which was the slightly lower clocked Radeon 8500 that only had 64 megs of RAM. And I was happy with it. Now, the Wildcat cards were primarily targeting workstation type users, so it'd probably be more fair to compare it to the price of a FireGL X1. And I looked and I could not find the release MSRP for those cards. If you can find or know how much one of those an X1 specifically cost back in the day, I would put it in the comments. I would love to know. I didn't spend a lot of time looking, but I found the price of the 3D Labs card in about a minute, and I spent maybe 10 minutes searching for the price of the ATI card, and I could not find it. Now, I don't have any of those original release cards, but what I do have are some of the follow-up cards that came out in 2003. This card is the cost-reduced VP9 P9 architecture, and this card specifically is the VP560. And I also have the flagship, the top of the line for this architecture, VP990 Pro. I haven't even opened this yet, so we're gonna have an unboxing, and I hope, because I ordered this on eBay, and I really hope that the right card is in here. I'm gonna be real sad if it's not. Now, they brag about this right on the box, that this card has a record-breaking 512 megabytes. And as far as I can tell, I did some research to try to confirm their claims, and I believe that this was the first card to ship with 512 megabytes of VRAM. NVIDIA wouldn't ship a 512 megabyte card until the Geforce 6800 Ultra in March of 2005, and AMD wouldn't ship a 512 megabyte card until the X800 XL in May of 2005. So, like 2 years later. It took 2 more years. So these Wildcats specifically were shipping in 2003. So this is what was the original box. It didn't have a manual. It does have the original, still sealed DVI to VGA adapters. It has the original driver disc, and the important thing, it has the card. And let's look and see if it's labeled on here in an obvious way. Yes, Wildcat VP990 Pro. Okay, so at least it's the right card. Huge pile of RAM aside, what makes these cards special? Well, in a word, programmability. This chip is a programmability beast. Like, I don't know any other word for it. According to the 3D Labs documentation, the Vertex processor, or what they call Vertex shading unit, supports conditional branches, loops, and function calls, much like the NV30. It is also capable of, quote, loading a program and context switching it to run it multiple times, unquote. Now, I've been developing graphics card drivers for over 20 years, and it's not 100% obvious to me what that means. Now, they follow that in the documentation with what feels like a pretty bold claim to me. The aim is to take a 3 megabyte RenderMan shader, similar to the size used for Toy Story, and have it compiled and running on P10 hardware. Now, I do have some questions here. 3 megabyte shader seems dubious. Like, how are they measuring that? Is that cannot just be shader code. Like, even Even shaders now aren't 3 megabytes in compiled code. That's... Anyway, but I think the concept that they're trying to sell up is that their vertex shaders can essentially be as big as you want them to be. Which is pretty interesting. Like, everyone else had a fixed, you could have this many instructions in your program, and you could execute at most some number of instructions. Now, both on Windows and Linux, there are ways of, if a shader is taking too long to execute, it will reset the GPU. Because if it takes too long, you just kind of assume, they've crashed, they're stuck in an infinite loop, some kind of bad news has happened. Now, that probably wasn't implemented back then. I know it wasn't in Linux. I don't know about in Windows. So I don't know how, like, what happens if your vertex shader takes 2 seconds or 5 seconds, or, I mean, if you're running a Toy Story shader, if it takes a minute. I don't know. Either way, being able to have very, very large vertex shaders at this point is kind of cool. Other parts of the documentation claim that the hardware can do various kinds of curved surfaces, including ATI's PN triangles from the R200. They also mentioned displacement mapping, and it says specifically the vertex array can access the frame buffer. It can store intermediate results, so operations too large to fit in the caches can still be processed. Now, to me, this sounds a little bit like a primitive form, perhaps, of vertex texturing. And I know on the NVIDIA side that the Geforce 6 was the first GPU to have vertex texturing. And I'm not sure about ATI, but it was... You got to keep up with the Joneses, so it was probably around the same time. So that would have been like the X850 sort of time frame, is my guess. I don't remember. I'd have to go look at the docs. But still, that's a pretty, that's a feature a couple years ahead of its time. And so all in all, the Vertex hardware sounds quite a bit more capable than the NV30, which was much more capable than the R300. Now, skipping from the front of the graphics pipeline all the way to the end, they have a thing that they call the pixel unit, and it sounds equally impressive. And I'm inferring from the documentation that what they call the pixel unit is what ATI and NVIDIA were calling raster operators, or ROPs, at the time. And so this on most hardware even now, this is a bit of fixed function, non-programmable. Generally, we'll make a distinction in parts of the pipeline as being either fixed function, which is it does a handful of things and you can turn some knobs to make it do different things, or programmable, that you can write some sort of a shader and have that shader run on it. Even now, for the most part, with the exception of, most hardware now can read from the frame buffer in the fragment shader, so maybe this is a little bit, but there's just a fixed function piece of hardware at the very end of the pipeline. Now, the 3D Labs documentation says that the pixel unit has a programmable SIMD array, and this implies that the hardware should be able to support any conceivable blending mode for combining the output from the fragment shaders with the contents of the frame buffer. And this, okay, that sounds kind of mundane and boring, but it's actually a pretty important piece of the pipeline. Now, imagine being able to do any Photoshop blending mode in hardware. Like, color burn in hardware in 2002 would have been pretty cool. We can do it now, because you can just directly read from the frame buffer and do whatever you want. But in 2002, that would have been pretty cool. And the hardware seems to even support programmable texture filtering. In the documentation that I have looked at, I have some more technical documentation that I haven't really dug through. But in the documentation that I've looked at, the details are a bit scant. It says something a little bit obtuse, like other less common filtering schemes can be programmed, as can virtually any filter that can be expressed as a shader. So, maybe you could do cubic upscaling filters in, directly in the texture sampling hardware. All right, that could be cool, but it's not clear to me if that means the sampling unit is programmable, or that there's enough flexibility in the shaders that you could sample a whole bunch of times from the texture directly, like sample a 4x4 block from the texture and implement a filter kernel in the shader code. It's not clear. Okay. So that's the good news. And now it's time for the bad news. Now, in the documentation that I looked through, I saw no mention anywhere of occlusion queries. And this is a feature where the hardware, when you're rendering triangles, if the triangles may be partially obscured by stuff that's already rendered, so you can query back from the hardware, I just drew a bunch of triangles. How many pixels were actually drawn to the screen? How many pixels actually got changed in the frame buffer? And it's a very useful feature for some rendering algorithms. And it's a required feature of OpenGL 1.5. And I don't know when it became a required feature of DirectX. DirectX 9.0 for sure doesn't have it, because notoriously Intel i9-15 hardware doesn't have it. And I don't know if R300 has it. I think R300 has. R200 I know doesn't. I don't remember about R300. I worked a lot on the open source Linux R200 driver, and I've done basically zero on the R300 driver. So I know quite a bit about R200 capabilities, but not as much about R300. So that's kind of a bummer. Now, one thing that is kind of frustrating about that is there's a lot of talk in their documentation about OpenGL 2.0. I think they were speculating about, very early on about what was eventually going to be in OpenGL 2.0, but they were definitely missing this 1.5 feature that would have been required for 2.0. There's not a lot of information about fragment shading specifically in the documentation, but I do see one thing that is very concerning and feels like a deal breaker. I had been so excited about this hardware. I had such high hopes of being able to write programs that would run on this hardware that, wouldn't run on an R300. But then the other shoe dropped, as they say. So in the documentation, it says there is 64 by 32-bit floating point texture coordinate processors and 64 by 32-bit integer shader processors. I don't like that word integer. I don't like that word integer at all. Now, traditional fixed function graphics pipelines operated on data that was floating point data, but it was limited to the range 0.0 to 1.0. And so that was implemented using integer math because it was a lot faster. You could, if you had a 16-bit value, 0 was 0.0 and 65,535 was 1.0. And so anywhere in between was some fraction of that. And so you could implement in hardware the math operations a lot more efficiently as small integer multiplies and adds and things. It was much, much cheaper. Now, R200 also used integer math for the fragment pipeline, but it increased the range allowed to minus 8.0 to plus 8.0. Now, on the other hand, R300 and NV30 both support full floating point in the fragment processing stage. The NV30 specifically supports both 32-bit and 16-bit float, as far as I'm aware, because you could decorate things with half in NV fragment program. And it's, as far as I'm aware, floating point is required by shader model 2.0. It's definitely required by our fragment program, and it's for sure required by later OpenGL 2.0 shading languages. This does not bode well. To me, the functionality of these cards, is in a weird in-between space where a product never should be. So it reminds me a bit of the Sega Dreamcast, which I was a huge fan of, but it came out in between, like pretty far in between generations of console hardware. And as a result, there were some things that people would come to think of as, no, that is a required feature of this generation, and why don't you have that? Oh, because you shipped way before everyone else. Well, okay. But you still don't have a DVD drive. You have this ridiculous CD drive that spins at 1 billion RPM. Let's talk some more about some of these missing features. I already had a guess that the card could only do DirectX 8.1 and OpenGL 1.4, but it's pretty lacking even there. It doesn't even actually do OpenGL 1.4. It's stuck at OpenGL 1.3. Now, the R200 that shipped way before could do OpenGL 1.4. And it came out like a year before. So here's what's even more weird about that these cards can't do OpenGL 1.4. This really, I'm going to go off on this for a while because it really bugs me. I don't understand. Somebody help me understand here. OpenGL 1.4 was made up of basically 15 extensions that got adjusted a little bit and brought into the core. And those can be divided into basically 3 groups. Functionality that's just software. Like, you don't need any special hardware support for this functionality. The driver writers just have to make the stuff work. On OpenGL 1.4 was also still a fixed function point of view of the world. And so if you have shaders, there are a bunch of extensions that are you just implement them in shaders. And so you just implement a few more instructions to do the thing, and it just works. This is the way that we implemented a lot of stuff for the R200. And finally, there's functionality that actually needs real hardware support. There are 2 extensions that need enhancements to the texture sampling hardware, 3 that need enhancements to the raster ops, and then there's stencil wrap. Now, of those, the P10 driver, of those 15, the P10 driver is missing 9. Like, I look at this list and I say, it should be 3 of those, I'll give it a pass on. I won't beat it up too bad. I won't quite give them a pass. But, even of those 3, I still have my doubts. Like, I think every NVIDIA and AMD graphics chip since 1999 or 2000 supported texture LOD bias. So that feels like a pretty huge oversight. The D3D report says that for the P10 says that texture mirroring is supported, but none of the various OpenGL texture mirror extensions are, like, none of them, even some of the very basic ones, are supported. So that seems weird. So looking ahead a little bit more, the picture is even more bleak. OpenGL 1.5 is 3 extensions, and none of them are supported. Our vertex buffer object, we started designing at that first OpenGL ARB meeting that I was at, and that was the first extension that I worked on. My name is listed in there. And it basically provides a means for applications to just allocate memory on the graphics card to store vertex data. That spec came out in February 2003, but by the time they were shipping the last drivers for these, like, there was no excuse not to support it. It's just ridiculous. Occlusion queries were a required part of OpenGL 1.5, and as far as I can tell, the hardware doesn't support it. And then there's another shadow functions extension that provides a method to do a couple different other kinds of comparison modes when using shadow maps. It seems like the programmable vertex programmable texture processor should have been able to handle this. I don't think it's actually that important of an extension. I don't know who was using that. If you know of a game or application that used those extra shadow functions, let me know about it in the comments below. I legitimately would be curious to know about that, because I'm not aware of anything off the top of my head. Not having vertex buffer objects is just rude. It's just rude. Like, ATI supported that extension on the original Radeon 7000 series, for crying out loud. Like the R100s. Like, the strangeness doesn't stop there. The driver advertises NV Vertex program and ARB Vertex shader, but not ARB Vertex program. Now, the former is the original Vertex programmability extension that ARB Vertex program was based on. It was the original NVIDIA assembly language for programming the Vertex unit. And the latter is the much more capable high-level language interface that would eventually replace all of those primitive assembly language ones. And our Vertex shader would go on to be one of the defining features of OpenGL 2.0. Now, there's the gap between NV Vertex program and ARB Vertex program is like about yay big. You know, your intern should be, if you have the one supported, the intern should be able to get the other supported in a couple weeks. Like, it is not a huge step from one to the other. Predictably, NV fragment program and ARB fragment program are not supported. Like, okay, the hardware does not have floating point support in the Vertex stage, so all right, those things need that. Instead, NV register combiners is supported. So they were able to, that was a very good strategic move, because there were a lot of games and other applications that wanted to use the NV Vertex programmability from NV20 and the fragment processing stuff from NV20. Like, people wrote a lot of stuff for Geforce 3. Okay. But ARB fragment shader is supported. What? What? ARB fragment shader is the high-level language analog of ARB Vertex shader. Like, you program the fragment pipeline in a C-like language, and it's like the other defining feature of OpenGL 2.0. How? Like, it requires more advanced functionality than those assembly shader things that aren't supported because the hardware can't. I'm flabbergasted. I don't know. I don't even know where to go with that. I'm going to do one thing with this hardware. I want to see, and then I'm going to finish this video up. I want to see in what modes this card will run Doom 3. I'm assuming, perhaps foolishly, I'm assuming that this will run Doom 3 out of the box. Doom 3 would run on, it had modes where it could run on R200 and NV20 class hardware using various OpenGL extensions. So it should also, wow, I never thought about that. It should also run on the Matrox Perhelia. Anyway, never thought about that. So it should be able to run on this in that mode using NV Vertex program and NV register combiners. Doom 3 also has a mode where it will use later versions of Doom 3. I believe had a mode where you could force it to run using GLSL. The default mode was it wanted to use ARB Vertex program and ARB Fragment program, which were the assembly language shaders that need floating point. Will these cards be able to run Doom 3 in the GLSL mode? I'm still just baffled. Now it is entirely possible that because the OpenGL version supported by these cards is so low that it's only OpenGL 1.3, that it might require some other features, and this may be a total lost cause. Should this be a lost cause, my plan for the follow-up video is I'm going to run a bunch of other stuff on it. I'm going to do a bunch of benchmarking with both cards that should completely wreck these cards in terms of performance. I'm also going to compare them against NV20 and R200. I have quite a few R200 cards, including FireGL 8800. And I have a bunch of Geforce 3s. I don't have any of the interesting Geforce 4s. Like, I have this cool, ridiculous, super rare Geforce 5, but I have nothing for Geforce 4s, which is weird. And then hopefully, time permitting, I'm also going to try to write some shaders and see if I can write something that will run on this and not on this. I don't know. We'll see. As an unexpected bonus, because this is a modern PC, the janky VGA video capture device that I bought actually works with this. You can see the capture of the display instead of me having to use my other camera to capture it, even though I did set it up. I did set it up. It is behind me, but I'm not using it. We're capturing VGA. All right, so we can look at, before I was talking about the OpenGL extensions, OpenGL 1.3, ARB Fragment shader. I'm still flabbergasted about that. Shading language 100. All of, with the exception of ARB Fragment share. Wow, that is really slow. Oh no, okay. So it does have register combiners and Vertex NV register combiners and NV Vertex programs. So weird stuff. So this is the 560 with 64 megs. It's the slower of the two cards. And I have configured this for OpenGL Games Default because I didn't see a specific setting in here for Doom 3. There's just the Games Default, and actually maybe it's back up higher. Let's see. Yeah, I don't see anything specifically for Doom 3. The drivers that I'm using are 3.01852. These are the most recent drivers that are on 3dlabs.com. It's amazing that that site is still up. I installed the Doom 1.3.1 patch, and let's see if this will work. We'll answer the question, can it run Doom? So it looks like the way that the capture is working, it does not enjoy 4:3, and I have not set up sound on this yet because I didn't care. All right, let's see. All right, let's okay. Okay, so it thinks low quality 640 by 480. Okay, I'm gonna turn the brightness all the way up because Doom. Okay, except I know the brightness. All right, let's see. Let's see if it runs. See if it runs and if it renders correctly. Fingers crossed. Now, I don't know what mode it's in, and I did not look up yet. I know there were some ways to... My memory is there were ways to force it to use specific rendering modes, and I don't remember how to do that. I'm going to have to look that up and check that out, especially for when I'm going to do some actual benchmarking. Oh, is it crashed? The loading bar is all the way up, but the computer's over here. Come on, little fella, you can do it. Oh, hey! It can do it. All right, I'm going to skip the intro because do the intro video. That doesn't... It's been a long time since I've played this from the beginning. That doesn't look right. Oh, wow. Even at 640 by 480, that frame rate is rough. So looking at how it's showing up, so the way it's showing up in the capture is about the way it looks on my screen, which is 10 or 15 FPS. That is pretty rough. Oh, okay. So the slowest of this family of cards can run Doom, and it's pretty rough. In my next video, I'm going to run Doom and some other games on both cards and on some other cards, do some benchmarking. It could also be this computer is a Pentium 4 2.4 gigahertz, so it's not a super fast CPU. I have a different much faster CPU that I'm going to run this on and do a bunch of comparisons. I'm going to write some software, see if I can write something that will run on this and not on the other, cards of similar generations. If you are interested in seeing that video, which I'm hoping to have it out in 2 weeks, it might be 3. I'm going to try to get it still in June, even though nobody else is doing GPU June. It's just me this year. If you are interested in seeing that video, I highly recommend that you click the subscribe button. If you enjoyed this video, I would really appreciate it if you would click the like button. And until next time, try to remember the good stuff.